All right, welcome to another edition of Mr. Strauss's Chemistry Corner. I know it's been a while since we've had a video, so I just want to say hello to my Polish friends, Cześć, and Guten Tag to my German buddies. And why don't we get started here with the kinetics. So I'm not going to go through all the problems. The number 11, the reason why intermolecular steps are seen so infrequently is because the probability of 3 molecules colliding with the right energy at the right orientation is very low. So usually you see uni and bimolecular. For number 13, the only thing that's going to affect the rate constant is temperature and catalyst, so B and C. Number 19, why don't all collisions result in a reaction? Because they don't have enough energy or they collide at the wrong orientation. Number 20, the catalyzed pathway is going to be E1 because the activation energy hill is lower. E1 represents the activation energy hill. Oh, actually, I think I'm looking at that wrong. E1, the blue line is the catalyzed pathway. The blue line is the catalyzed pathway. The purple is the uncatalyzed pathway. And E1 represents the activation energy hill of the purple line. And because the products are higher in energy than the reactants, it is a endothermic reaction, and E2 represents the energy difference between the products and the reactants. Number 26, we've got this reaction. And we want to try to find the coefficients. Now they give us the change in molarity. Now you could only have one rate, and okay, so you can only have one rate. So these numbers here have to be the same thing. But we know they're not the same thing because they told us that the change in concentration of A is 0.0080 molar, and the change in B is 0.0120 molar, and the change in C is 0.00160 molar. We don't know the time, but it's really not important because the time is going to be the same for them. But they all have to equal the same rate. So what we have to do is we have to multiply these by some number such that they're all going to equal the same rate. Okay? So if we look at the first one, it's a little bit easier. If I were to multiply this by 2, then this and this would be the same. Okay? So if the concentration of C is twice as big as the concentration of A, that must mean the coefficient of C compared to A is 1 to 2. There must be twice as much C being produced as A. It gets a little bit trickier with these two. So the ratio of this one to this one is 4/3. So in other words, the amount of this one is 4/3. Well, that's not a very nice ratio. So what would be easier then is if we multiply that through by 3. If we multiply it through by 3, then it becomes 3, 4, and 6, and now we have our answer. I think 59 is pretty self-explanatory. You can look that up in the back of the book. Number 61, I'll try to do that one quickly. So we've got the following reactions. This is a fast step, this is a slow step. So the slowest step is going to be your rate determining step, and that's what you're going to use to build your rate law off of. So because that's the slowest step, my rate law is going to be K concentration of C4H9Br. Since it's got a molar number of 1 out front, then I'm going to raise it to the first power. Okay. Intermediates in this reaction. Well, let's balance the overall reaction. Now that we have that, I'm going to go ahead and erase that. So, let's identify the intermediates first. So an intermediate is produced in one and consumed in another. So here is an intermediate, and here is another intermediate. So you have 2 intermediates in this reaction. Our overall reaction was going to be C4H9Br plus 2 waters, yielding Br1 minus plus C4H9OH plus H3O plus. So I'll just give you a chance to see all of its glory. Number 64, we are drawing reaction coordinates, and the first one has a delta E of 10 kilojoules per mole, positive 10 kilojoules per mole, and an EA of 25 kilojoules per mole. So if the activation energy is 25, it means our hill must be 25. And because it's a positive delta E, this height here between our reactants and our products must be 10. This is kilojoules per mole. That's A. For B, our delta E is negative 10 and our activation energy hill is 50. So we're going to have a bigger hill. Let's see how far down I can go. So a bigger hill, but we're going to get 10 out. So the difference is negative 10, so that's going to be an exothermic reaction. And the height of our hill is going to be 50. And for C, the change in energy is negative 50, and the activation energy hill is 50, so this is going to be quite a big one here. So the activation energy hill is 50. I should probably try to draw it to scale. So this is 50, and this is 50. So once again, an exothermic reaction because the products are lower in energy than the reactants. Number 69. The activation energy for the decomposition of Hi to H2 is 186. The rate constant at, so let's see here. Let's write a reaction down here first. So we've got Hi going to I2 plus H2, right? And it tells me the activation energy is 186 kilojoules per mole. And I'm at a temperature of 555 Kelvin. And my rate constant is 3.52 times 10 to the negative 7th. Okay. So we have all our information. Now what you're going to want to use is the two-point form of the Arrhenius equation. The two-point form is the ln of K2 over K1 is equal to EA over R, 1 over T2 minus 1 over T1. Okay. So that's the equation. So really we just have to plug in the numbers. And so ln of K2 over my first K1, the activation energy is 186 kilojoules per mole, divided by my R value, which is 8.31 joules per mole Kelvin. That's why we always put our units, because you'll see that those don't match up. So I'm going to have to convert that to joules. 1 over T2, my second temperature in the problem is 645 Kelvin. They want to know the new rate constant. And so now we just have to do a little bit of math. And let me get out my calculatrice. And of course I got the equation wrong. It's T1 minus T2. I knew I did something wrong as soon as I put it in there. So probably you all knew that before I did, that it's T1 minus T2 when you do that equation. So, try this one more time. So I got ln of K2 over 3.52 times 10 to the negative 7th is equal to 5.627. And if I'm going to get rid of the ln, I have to take the exponential of both sides. So then I end up with K2 over 3.52 times 10 to the negative 7th e to the 5.627. So that becomes 277.9 K2 over 3.52 times 10 to the negative 7th. So my new K value is going to be that. It helps if you use the right equations. And last but not least, number 75. We've got ozone being destroyed here. That's the slow step. That's the fast step. Overall reaction.